So last time we were talking about sequences in series, and I got a little too excited and went overtime, but we stopped here at rearrangements. And so this is the idea that addition, the order in which we do addition, is important when we're dealing with infinite sums. When we're dealing with finite sums, we have, commutativity, a plus b equals b plus a. And so that's not a problem. But with infinite sums, it's a problem. So, here's a little thought experiment to see, why that is. And so suppose we have some series, sum. And now what I'm going to do is I'm going to randomly pick the terms of the series and rearrange them. I'm going to add them in a different order. And so here, I actually went into R and asked it to randomly pick some numbers. That's how much of a nerd I am. And so here I have A66 plus A sub 879 plus A sub 1. This creates a new infinite sum with different partial sums. You can see the partial sums here aren't the same as A1 plus A2, A1 plus A2 plus A3. So these are different partial sums from the original infinite series. And so here, this is actually a different series. And this will, in theory, since the partial sums are different, the sequence of partial sums is different, the limit could be different. This could add up to something else, something different from the original series. So we have the original series up here that we started out with, and assuming it's convergent, it adds up to something. This rearrangement down here may not follow the same pattern of subsequences, because the partial sums are different. So yeah, so with the rearrangements, it's kind of irritating because it turns out that for series that are conditionally convergent, we can actually rearrange the series to converge to any number we want. And so if you're taking analysis, that's one of these weird things about series that, but this is specifically for series that are conditionally convergent. This is a series which converges, but it is not absolutely convergent. So it's conditionally convergent. And so the theorem, so this is the theorem from the old analysis book, which you don't really need to know, but this is just FYI. So suppose we have two numbers, alpha and beta, where alpha is less than or equal to beta, and they're both finite. Here, the equal is not a typo. So here I have equals infinity. That's not a typo. We can make the conditionally convergent series by rearranging it. We can force it to diverge. Analysis, it's a little weird. So yeah, so then the theorem says there exist rearrangements of the original series. And so I went with the old A tilde sub n and A hat sub n, right? I'm B hat, right? But I'm a mathematician. Anyway, such that the A tilde rearrangement can be rearranged so that it adds up to alpha, and the A hat rearrangement can be rearranged so that it adds up to beta. And this is just using the terms from this original series. We're just rearranging it. And because this is a conditionally convergent series, what the theorem tells us is we can rearrange it so that it'll converge to any number we want it to. And, that's irritating. So let me say this, the result about absolute convergence, and then come back to this rearrangement stuff. So for a series that's absolutely convergent, every rearrangement must converge to the same sum. So for a series that's absolutely convergent, the order in which we do the sum does not matter. For a series that's conditionally convergent, the order in which we do the sum does matter. And so very quickly, how does the proof of this result up here go with the rearrangement business? The idea is, if the series is converging conditionally, then it's not a series of all positive terms. If it's all positive terms, then the only convergence that's possible is absolute convergence. So if the series is converging conditionally, this is a series that's made up of positive and negative terms. That's the first thing to kind of reconcile, that this series must be a series that has infinitely many positive terms and infinitely many finite terms, negative terms, excuse me. And so now if you're allowing us to pick and choose, I can start by picking, for example, if I want it to converge to the number 3, which I'm picking at random. I pick all of the positive terms. I pick as many positive terms as I want until it adds up to 3. Remember, we have infinitely many positive terms to choose from. So eventually I will be able to gather up enough terms to sum up to the number 3. Once I get to 3, then I start adding a couple of positive terms, a couple of negative terms, a couple of positive terms, a couple of negative terms, and make the sum slowly as we go to infinity, get closer and closer, kind of hover around 3, you know. And so in this way, when you're dealing with a conditionally convergent series where we have a choice of infinitely many positive and negative terms, by selectively choosing these terms, we can manipulate what it converges to, what its limit is. However, for absolutely convergent series, that's not possible. And so this is why everyone loves an absolutely convergent series. It's all right if you want to cheer for the absolute convergent series right now. Take 2 minutes. Or not. So having said that, the ratio test and the root test are, you know, well-known tests to determine whether something is absolutely convergent. So for a ratio test, when it works, the conclusion you get is that the series is absolutely convergent. So how does the ratio test go? So, you know, suppose we have a series, sigma a sub n. Oh my God, that's me trying to write, y'all. So we take the a sub n term and we look at this ratio. We look at a sub n plus 1 over a sub n, look at the absolute value of that ratio and take the limit as n goes to infinity. So call the limit, you know, if the limit exists, call the limit r. And now if the limit is less than 1, then the series converges absolutely. And if the limit is greater than 1, the series will diverge. And if r is exactly 1, then the ratio test is inconclusive. We've gotten no information from the ratio test in that case, and we have to try a different test, like the root test, you know, or try and analyze it as a geometric series or use a direct comparison or a limit comparison. In this class, we'll mainly use like ratio test and geometric series. So you should know the concept of what a series is. So it starts, remember, a series is a special type of sequence, a sequence of partial sums. And then it doesn't hurt to familiarize yourself with geometric series, ratio test, root test, and we'll talk about power series here in a second. So actually, here's a great example of a power series, the Taylor series. So the Taylor series of the function f of x centered at the number x equal to a is defined as, and you remember this, or maybe you don't, you know, this good old, our favorite formula from Calc 2, the Taylor series formula, which says we have a sum from 0 to infinity. Here the coefficient, so the main thing I want to point out that's different with the Taylor series than the series we studied, you know, before this point, is the Taylor series has a variable in it. The Taylor series is a function. So the Taylor series may converge or diverge depending on our choice of x. So now let's carefully look at this Taylor series and let's, you know, differentiate the apples and the oranges. So here we have the sum from 0 to infinity. Here, this is a coefficient. Whoops, let me change that. I meant to do this. Here, this term is a coefficient. It's a constant. It's the nth derivative of f evaluated at the number a divided by n factorial, where n is our index. So n is 1, 2, 3, 4. And that term in the numerator, that's the nth derivative of f evaluated at a. And then the second part, this part has the variable in it. X minus a to the n, notice the x. So now I'm going to say, clearly, if x equals a, the Taylor series equals 0. And so, okay, this is our first example of a power series. So what's a power series? It's essentially a polynomial. It has this polynomial form, but it's, the degree goes to infinity. It's an nth degree polynomial, but we keep adding terms. That's a power series is essentially, a type of polynomial, right? An infinite degree polynomial. And so the Taylor series is our first, example of using series to capture functions, because ultimately that's what Fourier series are going to do. We're going to use Fourier series to capture functions that will be solutions to PDEs. So there's some subtle theory here. I want to explain this notation that I've got hanging out in front here. Notice what I don't write. And this is, something that may or may not have been emphasized that much in a Calc 2 class. What I did not write was I did not say this equals f of x. That's what my heart desperately wishes, but I don't know that for sure. So here, I'm going to put a question mark over here. So I did not write the Taylor series of f of x equals f of x, because in general, that's not true. That's a true statement for a certain class of functions known as analytic functions. So in complex analysis, we will learn that if you have a function that's analytic, then its Taylor series will converge to the function. But in general, that does not need to be true. So that's why I'm using this notation here. TS for Taylor series of the function little f, and then of x here to indicate it's the Taylor series itself is a function of x. And so that's part of the analysis that we will do with Fourier series. It's the same thing. I can take a function, I can find its Fourier series using some formula, but now, does the series converge? And if it does converge to the original function we started with? These are the analysis questions that we have to answer we'll answer these questions at the beginning of the class and then start solving PDEs. That's why, the analysis, if you're not used to it, can be a little bit dry. So the Maclaurin series is just the Taylor series, but we've centered it at 0. So A is equal to 0. So Maclaurin series is just a special type of Taylor series. It's a Taylor series centered at 0. And again, notice the notation here. I write MS for Maclaurin series of the function f, which is a function of x. The whole thing is a function of x. I don't say this is equal to f of x. I don't know at the face of it, I don't know if the Maclaurin series or Taylor series of a function will even converge. And if it does converge, I don't know if it'll converge to the original function that we used to create it. So of course, what we wish is that the function converges. I mean, the series, Taylor series converges, and it converges to the function that we created. So, and we'll talk about the theory for when that happens for Fourier series. So, so I say here that the Taylor series may or may not converge, and if it does converge, it may or may not converge to f of x. The interval of convergence, so this is now how we start to quantify the convergence behavior of a power series. So when we start to talk about the convergence of a power series, that's with respect to what we call an interval of convergence. And so how do we practically find the interval of convergence? That's when ratio test or root test comes into play. So I can use the ratio test or root test on the Taylor series to determine what the interval of convergence is, if it has an interval of convergence, and then we can then start to address the issue of convergence. What does it converge to? So we're sort of spoilt in the sense that some of the functions we're very, very used to working with are analytic functions and very well behaved. Like e to the x, its Maclaurin series converges to e to the x for all real numbers. Like, wow, that's really nice. Thank you, e to the x, you know. So we have to be careful of our assumptions that the series, when we have a series, that it'll converge. And if it does converge, that it'll converge to, you know, what we originally started out with. Those are all things we have to watch out for. So the interval of convergence procedure is very simple. You take this term here. You know, I don't want to review too much of the Calc 2, so I would have you kind of just look it up in your calculus book or online. But essentially, you take this term here, and this entire term is the a sub n in our ratio test. So this whole thing, the entire term that makes up the Taylor series, this is the a sub n that I'm going to stick in here in the ratio test. So you do a ratio test, you take the limit that you get, you set it less than 1 and solve for x. Okay, so that's the basic procedure. Take that entire expression there, that's the Taylor series thing, take a ratio test of it, take the limit. Once you get the limit, set it to be strictly less than 1. And don't forget the absolute values. Set it to be strictly less than 1 and solve for x. That'll give you an interval. And there's a problem like that on the homework. You just find the interval of convergence. So the other thing, okay, yeah, Alana.
Can you do the same thing for a Maclaurin series, or is that only for a Taylor series?
Yeah, you can do that procedure with any power series.
Okay, cool.
Yeah. So, you know, the lecture that we're involved in right now is review, right? So now I'm going to slightly switch gears from sequences and series, not in a very smooth way, but now I'm going to switch to different coordinate systems. So why would we be interested in different coordinate systems? So some of the PDEs that we're solving, depending on the shape of the domain, so every PDE we solve will have a domain shape. And so, for example, if the shape of the domain is circular, it would be better to use polar coordinates, you know, as you know how polar coordinates work. And if we're doing a 3D PDE and the shape of the domain is a sphere or a cylinder, you know, then we'd want spherical coordinates or cylindrical coordinates. Okay, so I want to review a little bit of your polar coordinates. Okay, so I've got the axis here. It helps to just think about the picture. I've got the axis here, and we've picked a point x, y. So you know, in Cartesian coordinates, we can identify the point with the x coordinate, which is the horizontal distance from the origin, and the y coordinate, which is the vertical distance from the origin, with an orientation. I shouldn't use the word distance because that's always positive, right? So here, x could be plus or minus, right? With an orientation to the right or left, above or below. For polar coordinates, what we can do is we can uniquely identify, well, I shouldn't say uniquely, we can identify the point in space as being the intersection. So there's two things happening here. There's a circle. So let me try and get this circle the right size. It's never going to happen. There's a circle of radius r that the point lives on. And there's what we call a ray. So a ray is a line emanating from the origin. So here's the ray from the origin. And you know, from the origin, we have infinitely many rays emanating. Think of the origin like the sun, and these are rays coming out of the sun. And then there are circles around these rays. And at the intersection of a ray and a circle, we can find the point. So here, you know, at the intersection of some circle and ray, there's our point. Our point is, now we can identify, you know, that point using the radial distance. So here, r is this distance from the center, this radial distance r. And you can use the old distance formula. You remember positive square root of x squared plus y squared equals, will give you your radial distance. And then we can use this angle theta here also. So between r and theta, I can identify the point. And you remember how polar coordinates go. So this essentially boils down to trigonometry. Here, we can show that cosine of theta is x over r. So x equals r cosine theta. You remember this. This is just from trig. It's like watching a baby learn how to write. And y, as you remember, just from trig again, sine theta would be opposite over hypotenuse y over r. So y is r sine theta. So yeah, and then, the other way, r is the square root of x squared plus y squared, and tangent theta equals y over x, right? So polar coordinates, we'll use them as necessary. It's not like the class is going to be all polar coordinates and spherical coordinates for the whole thing. We'll use them once in a while here and there. So you just need to, be aware of them. Oh yeah, so here are the formulas. I don't know why I wasted all my time writing. Well, it was not a waste. I'm practicing, I'm learning. So here are the formulas that go back and forth. And these are just from trig, right? We shouldn't overcomplicate these things. This is just a triangle. This is just a right triangle. And these are just the formulas that relate all of our trig functions and our Cartesian functions. The spherical coordinates, the way that works is now we're in 3 dimensions. So I'm not on the plane anymore. I'm in space. So now pick a point here in space. I've picked a point here in space. Okay. This point, it has a shadow. So that in the XY plane. So we define the angle theta to be the same angle theta as in polar coordinates, but it's for that, if you projected the point in space down to the XY coordinate and drew a line, it would be the angle with the polar axis, and the shadow of that point is your angle theta. You can see from the diagram. And then we define, instead of r, we have in the polar coordinates, we have the radial distance, the distance from the origin. So we use the Greek letter rho. So, rho starts with r, like the word radius, but r was already taken for the polar coordinates, so we went with rho. Seemed like a natural choice, or not. So yeah, so rho is just the distance from the center. So this would be the positive square root of x squared plus y squared plus z squared, just your distance formula, distance from the center. Finally, there's an angle here with the z-axis. And that angle, so let me get rid of this circle here. There's this angle here with this, that any line through the origin and the point in space makes with the z-axis, and that's called phi. And so with these 3 coordinates, we can identify a point in space. It's essentially an intersection of a sphere, a ray through the origin, and a cylinder. The theta in the XY axis defines a cylinder. So here, if you have a circle here, that becomes a cylinder. The rho defines a sphere. I guess the phi defines a cone, maybe, and then we have the line through the origin, and so all those things intersect or something like that. But yeah, so the phi, typically when we teach it, we think of the phi as an upside down umbrella, like this. And so the angle, like when the umbrella is totally open, the angle is 90 degrees. And when the umbrella is totally closed, the angle is 0. And so this angle of the umbrella is our phi. And so this is the traditional way we used to teach But I don't know, do we still have umbrellas or did like a app replace that? Do you guys know what an umbrella is, damn it? Anyway, I'll just keep moving. So here again, the formulas to convert from one to the other, they look complicated, but they're not. There's two triangles here. So this is just kind of two pieces of trigonometry. You've got a triangle down here, just like the triangle that's, you know, from polar coordinates. And we have a triangle right here. And so between those two triangles, you can come up with these formulas. And, you know, we don't really even use spherical coordinates that much from what I remember. We use it for setting up a model, but so I wouldn't worry about it too much. It's not like the whole class is spherical coordinates. Okay, so this is just to remind you, you know, so that when we see it later, you're like, oh, okay, yeah, spherical coordinates. So the other thing I'm switching over now, because this is still part of review. So yeah, you will see some polar coordinates on the homework. And it's actually combined with chain rule. So this is a good thing to talk about here. So because we are dealing with partial derivatives, that involves chain rule from time to time. Okay, because this is not a ODEs class. We're not, you know, dealing with regular derivatives. This is a PDEs, right? Partial differential equation. So let me remind you of chain rule. So suppose Z is a function of X and Y, and X and Y themselves are functions of two other variables, let's say R and theta. You know, here, these aren't necessarily the R and theta from polar coordinates, but they could be. If you want, for an example, you could say, yeah, suppose X equals R cosine theta and Y equals R sine theta, for example, but it doesn't have to. So then you remember how this goes, and it helps to have this variable tree here. So I would actually look at the tree first before we look at any formulas. So here, we're interested in two things. We see at the ground floor, you know, F is a function of X and Y, but X and Y are functions of R and theta. So at the end of the day, we want to ask about what's the derivative of F with respect to R? What's the derivative of F with respect to theta? Those fundamental underlying variables. So the variable tree here shows us the chain. So if I want to find partial F, partial R, or partial Z, partial R, here Z equals F. So I want the partial R derivative. So here, there's two branches that we can follow. So I can go partial Z, partial X, and then partial X, partial R. That gets me to the R variable. Or I can do partial Z, partial Y, and partial Y, partial R. And so now if you look at the formula I've written here, that's what we have. So here now we can look at the formula it'll make. So you can see here's the first leg of our journey along the X branch, partial Z, partial X, and then partial X, partial R gets us to the R variable. And then we have the second branch of our journey along the Y variable, partial Z, partial Y, and then partial Y, partial Y. So for me, having the little diagram helps a lot. And then similarly, for the theta variable, again, there are two paths right here. I can go down the X branch here, partial Z, partial X, and then partial X, partial theta, or partial Z, partial Y, partial Y, partial theta. And so that's what we have here in the second set of formulas. So then, depending what the functions were, so for example, that's right, I'm gonna write. For example, if X is R cosine theta, then partial X partial R would be the derivative of R cosine theta with respect to R would be just cosine theta. If X is R cosine theta, then partial X partial theta would be negative R sine theta, right? So chain rule. The diagram helps. You just kind of, follow it through. And then the notation is set up to kind of help us make sense of it. we shouldn't think of these partials as fractions, and we shouldn't think that we can cancel these two, but the notation is set up to kind of, so that we can sort of think about it that way. It's just set up that way to aid our brain in dealing with the concepts. So remember, those aren't fractions. That a derivative is a limit of a fraction. So those are limits that we're looking at, convergent limits. So there's a theorem from Calc 3 that we're going to need like one time, but there's a lot of geometry involved, and so I have to build up to it. It's basically the fundamental theorem of calculus. So from Calc 1, and I'll talk about that in a second. It's basically the three-dimensional version of the fundamental theorem of calculus from Calc 1. Okay, so what I'm going to now do is give you three definitions that are building up to a theorem called the divergence theorem that you studied in Calc 3. Okay, so first of all, we need this concept of what's called a vector field. So a vector field is like a function, except for any point in the plane or space. So here I'm looking at a three-dimensional vector field. So any point in three-dimensional space, we associate a vector to it. We associate something, that has direction and magnitude. So you're in a vector field right now, right? Otherwise you'd be floating around, right? So we're in a gravitational vector field right now, all of us. At least I am. I don't know. I saw one person's coffee mug go floating by, so I don't know. So the gradient now, so we have a vector field. The gradient is kind of the analogous version of a derivative. If you think of a vector field as kind of like a function, for a function we have inputs and outputs. The input's a real number, the output's a real number. Here, the input's a real number, the output's a vector. So if you want to think of a derivative, what would the derivative of a vector field be? What's the analogy of a derivative for a function? It's what we call the gradient. So here, if f of x, y, z is some surface, then what we call the gradient vector field of f is going to be this vector down here. That's del f, which is, it's the x partial, y partial, z partial put into a vector. So each component has the rate of change information in that direction. Yeah, is there a question? So if the gradient tells us how the surface, so f is a surface, and so the gradient has the sort of rate of change information for the surface in each of the x, y, and z directions. And you remember the gradient from Calc 3. It can be used to determine a tangent plane. So one of the traditional pictures is if we have a sphere, if you pick any point, you can define a tangent plane, a plane that just touches it at a single point. And the normal vector that's defining that tangent plane, we can use the gradient vector to find that normal vector. So the gradients would be along the tangent plane. The gradients describe the slope of the tangent plane. It's like trying to tile a spherical object. The tile would be like a tangent plane, and the slope directions of the tile would be your gradient vector. We also have a thing called the divergence, which is basically, this is kind of like the derivative. The derivative gives us the rate of change information and direction information. So the gradient is kind of the direction information, and the divergence is kind of like the rate of change. So here we're just summing. So if I have a vector field fxy, so here the input is a point, the output is a vector. The divergence is just the sum of the partials of each of the components in that direction. So partial p, partial x, p is in the x component. Q is in the y component, so we do partial q, partial y, and r is in the z component, we do partial r, partial z. So typically, what we will do is look at the divergence of the gradient gives you a differential equation. So that's, at the end of the day, that's how this stuff, if you take So the Laplace equation, so if you take the divergence of the gradient, that gives us a PDE. This is a PDE. And so if you want to say, how do we get, from Calc 3, how do we get to PDEs in a natural way? This is a natural way. The divergence of the gradient gives us what we call the Laplacian. And the Laplacian, is a fundamental PDE that we will study. Okay, so here's the divergence theorem. Here's the divergence theorem. And if you haven't seen this in a while, give it a little time, let your brain start to remember and you start to go back and think about those things. But this isn't all like a Calc 3 class. I don't want you to be worried. It's mostly 2D stuff. We majority of the time we're doing 2D stuff. So, okay, here's the divergence theorem. I'll show you the divergence theorem. It's good to look at the picture at the bottom. And then it's even better to wait for the fundamental theorem of calculus. Okay, so first let's just understand the statement here. E is a simple solid region. So this thing, E is a simple solid region. What looks like a partial symbol here, partial E, that's the boundary of E. So that's the shell. That's the shell. That's the boundary of the surface E. And now what we have is we've got a positive outward normal vector. So what does that mean? We have a function n. It's a vector. So for any point you give me, it'll give me a vector. And so for any point you give me on the surface, n will give me an arrow that points directly, outward. And that's kind of perpendicular to this area, as if you kind of smoothed it out a little bit and flattened it, they'd shoot an arrow out. That's n. That's called an outward normal vector. There's also an inward normal vector, but we're using the outward. So this gives us an orientation. So this way I can have a sense of what is up and what is down. So if you're ever scuba diving and you see the bubbles going down, guess what? You're upside down, right? This is why people should never go swimming when they're drunk, right? So they lose their orientation. Their normal vectors are all messed up. So if F is a vector field now, okay, so suppose we have the gravitational vector field, we have some vector field. The divergence theorem says, so here, let's go very slowly. The divergence here, that's like a derivative, okay? That's like the derivative of the vector field. And so here we're adding up the derivative of the vector field inside the surface. So one of the most important things I want you to notice is what we're integrating over. Here we're inside the surface and we're summing up the derivative or divergence here of this vector field. And so the divergence theorem tells us, well, that's equal to this double integral, but be very careful. This is actually a surface integral. See, this is an integral over the surface of the 3D object. And here we're able to figure out the sum of the divergence inside the object by summing the normal component of the forces coming through the surface. If you think of a net and fluid passing through the net, here at the net, we're looking at the outward force times the area of the surface. So ds here is calculating the surface area. And so I guess you can look at the picture here. It's going to calculate the surface, take the normal component of the force and multiply that. That, if you add it up all over the surface, that should be equal to the sum of the derivative, the rate of change, the divergence inside the surface. So hold on, let's look at the fundamental theorem of calculus. So you remember, we said the integral from a to b of the derivative of f of x dx is f of b minus f of a. So actually, I don't like to think of it as f of b minus f of a. I like to think of it as -1 times f of a plus 1 times f of b. So what's that about? So here, this interval, you can think of the interval as the solid region E. The surface would be the endpoints, would be the surface. And so look, I'm trying to calculate the sum of the derivative inside the interval. We can do that by looking at what's happening at the boundary. We're taking the outward normal. So here, -1 is an outward normal. Think of that as a one-dimensional vector. That's a one-dimensional vector. It's a vector that just lives in the real line on the x-axis, pointing to the left. That's an outward normal. And look here, n equal to 1 on the other side, that's also an outward normal. So this is about being able to say something about the rate of change of some, vector field or the function inside a domain by observing what's happening to the, integral of that, not the derivative, but the actual function on the surface. So here's like the really stupidest way I think about it. Okay, this is how I explain it to my Calc 1 students. And it's like the stupidest thing ever, but I don't know, it kind of makes sense to me. So I'm going to tell it to you. So you know how they have the club or the club? I don't know what your kids are calling it. So suppose I want to count the number of people in the club or the club, right? So there's two ways to count the number of people in the club. Okay, stay with me on this. Stay with me. This will go somewhere that'll make sense. We could be inside the club, right? Kind of monitoring the rate of flow, kind of counting how many people are coming, kind of, inside the club, monitoring the rate of flow, kind of calculating how many people are coming in per minute, sort of an idea, right? That's one way, to be inside the club. Or if you don't want to get shot, you could be outside the club, counting the number of people that go in and subtracting the number of people that go out, right? So that's what we have here. That's what we have, that's the way I think about it. It's kind of stupid. So one way is to, from the outside monitor, from the inside monitor, how many people are coming by, sort of monitoring the rate, how many people per minute or something like that. It's a kind of loose analogy. The other way to do it is to just keep track of the ins and outs. How many people are going in, how many people are going out. In both cases, we're counting the same thing so that they're equal. And so here we have the fundamental, oops, sorry, wrong. So here we have the fundamental theorem of calculus. On the left-hand side, I'm calculating something from inside the domain. On the right-hand side, I'm calculating the same thing from outside using the surface information. And that's what, and I'll stop here in a second. And that's what this divergence theorem is saying. It's the same thing, but kind of a 3D version. And here, F is a vector field, and we're kind of using the rate of change information, all added up together in each specific component. We're relating that to the force component on the surface. Okay, so yeah, again, we won't use this every day. We'll use this like one time or two times, so it's just to be aware of the ideas. All right, I still actually have a couple minutes, I think. So how many minutes do I have? I don't know, like I can't see that clock on my computer.
5.
Oh, okay, good. So all right, let me just talk for like 2 minutes about this slide and I'll stop. Okay. And this will, so we've covered a whole bunch of stuff that'll help you on your homework. So right now already you can do 4 of the 5 problems, okay, especially if I talk about this. So, and I'll send out the lecture from Monday. I'll put that out early so that if you want to read ahead, you can read that. And there's one question on that from the homework. And the homework will be due a week from Friday. So just, so you'll have all that information up front. So let's now switch gears again, right? We did Calc 1, we did Calc 2, we did Calc 3. So now we're at ODEs. So next stop will be matrix methods, right? So for ODEs, I just want to solve this first order differential equation. Okay, and I'll stop here. But so for this first order differential equation, dy dx equals negative alpha times y. It doesn't have to be negative. It could be just any constant times y. Okay. So first, obviously note that y equal to 0 is a solution. So that's called a trivial solution. What we would like to find is a non-trivial solution, a non-zero solution. So we'll use what's called separation of variables. This is the ODE technique, separation of variables. We will also do separation of variables in PDEs. It's slightly different. Not that different, but slightly. So here, we start with our derivative is y prime equal to minus alpha y. And now move, so this is the separating of the variables part. We put all of the y variables on one side, everybody else on the other side. So I move the y over y of x to the other side here, to the left side. And so on the left side now we have this quotient y prime over y equals negative alpha. So now y prime over y, this is actually the derivative of the natural log of the absolute value of y. So if the absolute value throws you off a little, that's something you should maybe review, take a look at a calculus textbook, or I can talk about it next time. But for now, remember that the derivative natural log of u, for example, is u prime over u. Actually, that's true of the derivative of the absolute value. Because if you have a negative u, then derivative of negative u is -1 over minus u, the minuses cancel. Okay, so anyway, I'll let you think about that. So here, the integral of y prime over y, or you can think of y prime over y as being the derivative of the natural log of y. So then we can integrate both sides. If we integrate both sides, here I lose the derivative. On the other side, I get minus alpha x plus c. And I'm going to call it c tilde because I'm going to replace the c tilde with a c in a second. Okay, so I want c to be free. So, but yeah, it's, you just integrated both sides. I get natural log of y equals minus alpha x plus c. Okay, so now raise both sides to e. Okay, so I'm going e to the ln blah blah is equal to e to the minus alpha x plus c. And the e and the ln cancel. So I just get back absolute y of x equals e to the minus alpha x plus c, which I'm going to break up the variable part and the constant. So I write it as e to the minus alpha x times e to the c tilde. Finally, I drop the absolute value bars and I do a plus minus here because the absolute value of this plus minus will get me, back to y. So I drop the absolute value bars, say y equals plus minus e to a constant times e to the minus alpha x. Okay, so we're almost done here. Finally, I just say that plus minus e to a constant is itself just a constant. So I'm just going to replace that whole thing with c. So here's our solution to this first order differential equation, y of x equals c times e to the minus alpha x. And we can verify that it's a solution, so I can indeed check that it satisfies the actual differential equation. So I can take the function, plug it in for y. So here I've plugged in the function for y, and that's the derivative. And I've shown that it's equal to minus alpha y. So I've shown that the differential equation has been verified. Okay, folks, so this is the general solution of this ODE. And some questions for the future is, how do we know that this is the only solution? And those are some analytic issues we'll talk about with regards to PDEs. So I'm going to stop right here.